When Pluto was officially reclassified from a full planet to a dwarf planet in 2006, it felt like the end of a story for many people. For decades, Pluto had been known as the ninth planet of our solar system, a distant icy world at the edge of everything we knew. But suddenly, it was removed from that list and redefined as a small, frozen object in the Kuiper belt. At the time, this change made Pluto seem less important. Many thought of it as a cold, inactive remnant from the early solar system, just another icy rock drifting in darkness, far away from the Sun, with little to offer science. But that perception is now changing in a major way. With modern space missions and advanced telescopes, scientists are discovering that Pluto may be far more active, complex, and interesting than anyone expected. Instead of being a dead frozen world, it may actually be a dynamic system with internal heat, surface activity, and possibly even hidden oceans. One of the most famous regions on Pluto is called Sputnik Planitia. It is a massive, heart-shaped plain made mostly of nitrogen ice. From space, it stands out immediately because of its smooth, bright surface and enormous size. But Sputnik Planitia is more than just a beautiful feature. Its massive weight and structure appear to affect how Pluto rotates. In fact, it seems to play a role in balancing the entire dwarf planet, almost like a natural weight system that influences its orientation in space. This alone suggests that Pluto is not just a simple frozen rock. Its surface and internal structure are connected in ways that scientists are still trying to understand. Even more intriguing is what may lie beneath this icy surface. Many scientists believe that Pluto could have a subsurface ocean hidden under layers of ice. This ocean would not be made of ordinary liquid water on the surface, but a deep internal sea trapped beneath the crust. The idea might sound surprising, especially for a world so far from the Sun, but there is a possible explanation. Pluto's interior may still contain heat left over from its formation billions of years ago. On top of that, radioactive elements inside its rocky core could slowly release energy over time. This combination of heat sources might be enough to keep water in a liquid state deep underground, even in such an extremely cold environment. If this is true, it completely changes how we think about Pluto. Because where there is liquid water, there is always the possibility, at least in theory, of life. This does not mean Pluto definitely has life, but it opens the door to a very important scientific question. Could life exist in environments far beyond Earth, in places completely unlike our planet? Supporting this idea, data from NASA's New Horizons mission, which flew past Pluto in 2015, revealed a surprisingly active surface. Instead of being smooth and ancient, Pluto's landscape is filled with mountains, valleys, fractures, and shifting ice regions. Some areas look relatively young, meaning they may have formed recently in geological terms. These features suggest that Pluto is not frozen in time. Its surface may still be changing, shaped by forces coming from inside the dwarf planet. Another major clue comes from Pluto's relationship with its largest moon, Charon. Unlike most planet-moon systems, Pluto and Charon are unusually connected. Instead of one orbiting the other, they both orbit a shared center of gravity located in space between them. This makes them behave almost like a double planet system. This close gravitational relationship creates tidal forces between the two bodies. These forces may generate internal friction and heat inside Pluto, adding another possible energy source that keeps its interior active. Some scientists believe this tidal interaction could even help maintain a hidden ocean beneath the surface, if one exists. There are also more speculative ideas about what such an environment could contain. If a subsurface ocean exists, it might host microbial life forms adapted to extreme conditions, complete darkness, freezing temperatures, and enormous pressure from layers of ice above. These organisms, if real, would be completely different from life on Earth, surviving in a world without sunlight. This kind of possibility has captured the attention of researchers like physicist Brian Cox and others who study planetary habitability. Even the discovery of simple microbial life in such a place would completely change our understanding of where life can exist in the universe. But Pluto's mysteries do not end there. Its atmosphere, although extremely thin, is surprisingly active. It is mainly composed of nitrogen, with small amounts of methane and carbon monoxide. When sunlight interacts with these gases, it creates complex organic molecules known as tholins. These tholins give Pluto its faint reddish haze and are especially interesting because they are linked to prebiotic chemistry, the kind of chemistry that may have played a role in the origin of life on Earth. Even Pluto's moon Charon adds to the mystery. Its surface shows deep canyons, fractures, and unusual polar regions with reddish deposits. Scientists believe that some of these features may be caused by material escaping from Pluto and slowly accumulating on Charon over long periods of time. This creates a strange relationship between the two worlds, as if they are sharing material across space in a slow, continuous exchange. When we look at Pluto as a whole, it stands out strongly from other objects in the Kuiper belt. Most of those distant icy bodies are cold, inactive, and unchanged for billions of years. But Pluto appears different. It shows signs of movement, internal heat, and ongoing geological processes. This makes it one of the most scientifically interesting objects in the outer solar system. And yet, despite everything we know, Pluto remains largely unexplored. We only had one close visit, NASA's New Horizons flyby in 2015. That mission gave us our first detailed look, but it was only a brief snapshot in time. To truly understand Pluto, future missions will need to go further. Scientists hope for orbiters that can stay longer, map the surface in detail, study its atmosphere, and perhaps even investigate what lies beneath its icy crust. There is even ongoing speculation about whether Pluto might have a weak magnetic field. While there is no direct confirmation yet, some indirect observations suggest there could be internal processes capable of generating magnetic effects. If true, this could help protect any internal ocean from solar radiation and help preserve its chemical stability. Pluto's position in the far outer solar system also exposes it to unusual influences. Gravitational interactions with other Kuiper belt objects, along with ancient collisions, may have shaped its structure over billions of years. Some of these processes may still be active today, slowly reshaping the dwarf planet. All of this leads to a very different picture of Pluto than the one we once had. It is no longer just a cold, dead object at the edge of the solar system. Instead, it appears to be a world full of contradictions, frozen on the outside, but possibly active on the inside. A place where ice moves, chemistry evolves, and internal heat may still be shaping its future. And perhaps the most important question is not whether Pluto is active today, but what it is still hiding beneath its frozen surface. Could there be an ocean beneath the ice? Could there be chemical processes we do not yet understand? Or could Pluto be one of many hidden active worlds waiting to be discovered in the distant darkness of the Kuiper belt? As our technology improves and future missions venture farther into space, we may eventually find the answers. Until then, Pluto remains a reminder that even in the coldest, darkest regions of our solar system, there may still be worlds full of surprises waiting to be uncovered. So the question remains, what is Pluto really hiding beneath its icy shell? And how much more is still waiting for us in the outer solar system?